Despite the broad and often overwhelming amount of self-acclaimed best performance nutrition plans, there is one debate that remains ever contested and central to many more niche or specific options. That is the debate of fat versus carbohydrates. Today, my intention is to hone in on this debate, specifically on ultra endurance sport. I'll explore the fundamentals of each for both training purposes and adaptation. So, traditionally, high carb, low fat diets have been a commonly accepted norm for ultra endurance athletes, and not until recently have athletes, nutritionists, and coaches begun to take notice of the contrary high fat, low carb diet. Typically, a high carb, low fat, or traditional dietary option consists of a carbohydrate intake of around 45 to 65% of total daily caloric intake, which is broadly 5 to 12 grams of carbohydrates per kilogram of body weight per day. Contrastingly, high carb, low fat diets propose a carbohydrate intake of less than 25% respectively, and a fat intake of greater than 60%. So, what is the essence of each? Carbohydrate diets have been seen as and remain essential. Carbohydrates have been seen as and remain essential as a source of fuel for bodily functions. Carbohydrates provide the body with glucose, which is then converted into energy. This glucose fuels both brain and muscles during exercise and recovery and everyday functions. There is no absolute substitute to glucose in that regard. The excess glucose is produced by the small intestine and then stored as glycogen, a reserve of carbohydrate used to maintain blood sugar and energy levels during periods of increased energy demand, for this case, exercise. The necessity of carbs, however, comes in the ease of use and the efficiency in the body's ability to break them down. It is additionally essential to replenish glycogen stores post-exercise to support muscle protein synthesis and provide the body with fuel for recovery. Given this, why would one consider a high-fat, low-carb diet? The body utilizes triglycerides, which are our fat stores, as the primary source of fuel at low intensities, below the lactate threshold, referred to as fat metabolism. We can see this on the graph provided. This occurs at around 45 to 65% of VO2 max. This is important to us because the body stores upwards of 60,000 calories of triglycerides or fat compared to an approximate 2,000 calories of glycogen at any time. The principle is therefore that due to our body's almost endless fat stores, the use of fat as a source of fuel will provide an endless store, avoiding the symptoms of carbohydrate deficiency such as fatigue, dizziness, or lethargy in prolonged exercise forms. So, how does this work? The skeletal muscle consists of type 1 and type 2 fibers. These both have differing abilities. Type 1 fibers have high mitochondrial density and therefore prefer oxidation for ATP production. This is the primary source of fuel for these muscle fibers, is therefore fatty acid oxidation, and are engaged during low intensity exercise where lactate levels remain minimal. Type 2 fibers, contrastingly, have a lower mitochondrial density, thus relying on glycogen stores for their ATP production. These fibers are activated when the intensity activity is high, above our lactate threshold. However, the scope of this debate is more broad than you could cover in 6 hours, so I'll be honing in on the strategies employed by ultra-endurance sport athletes and coaches. The relevance is that the ultra-endurance sports training and racing is done predominantly at a low intensity, relying heavily on type 1 muscle fibers. Thus said, the choice of word heavily should not be confused as exclusively in that regard. So, this naturally brings out the next topic, which is metabolic flexibility. This is a hugely emphasized point in training and racing in ultra-endurance athletes, and I view this principle as imperative in this discussion. Although it is not definitive as the best way forward, it provides a great starting point. Metabolism refers to the whole sum of reactions that occur throughout the body within each cell and provide the body with energy. Arturo Sanchez. Metabolic flexibility is effectively the ability to use both fat and carbohydrates, triglycerides, or glycogen, as fuel at varying levels of exercise intensity and availability. Thus, it is the body's ability to choose triglycerides or oxidation as the primary source of fuel at certain intensities and availabilities. Metabolic flexibility is in essence the body's capacity to turn triglycerides or fat oxidation for the larger portion of exercise requirements in a more efficient manner, an increased rate of oxidation, and at higher intensity exercise. This allows for the preservation of carbohydrate until the body reaches intensities unsustainable exclusively by fat oxidation, ultimately increasing the time to exhaustion and our capacity to perform without fatigue. So, where does diet come into this? There are a magnitude of factors, both inherent and through manipulation, for lack of a better word, including nutrition timing, seasonal dietary plans, intermittent fasting, and a variety of others that can contribute to changes in metabolic flexibility. Firstly, high fat diets. Studies have shown that a high fat, low carb diet in lean subjects could increase fatty acid oxidation at the expense of expending glucose. Additionally, there were increases in expressed genes involved in fatty acid transportation and oxidation. And finally, subjects in the study have demonstrated a retained capacity to use triglycerides as a source for higher rates of exercise. For example, some athletes are able to generate 50% or more of their energy requirements from fat oxidation at exercise intensities up to 90% of their VO2 max, increasing the crossover point of substrate utilization, the crossover point between triglycerides and glycogen. Thus, high fat, low carb diets can promote the higher rates of fat oxidation at a variety of speeds and intensities. Drawing back on ultra endurance sport here, we're unlikely to be training at above 85% of our VO2 max very often, if ever. So we may be able to promote increased fat oxidation in all of our training, noting that this remains not exclusively fat oxidation again. However, triglycerides will be fueling more of our needs, resulting in hopefully less lactate production and, in principle, pushing out our time to exhaustion through carbohydrate deficiency over long periods of exercise. Noting additionally that if our racing goals require high intensity needs, periodization of high fat diets may be a better option, allowing adequate carbohydrate consumption and glycogen storage as training and racing needs become more intensive and closer to the VO2 max more regularly. Another alternative, intermittent fasting, is another way of improving metabolic flexibility. During sleep, circulating carbohydrates is in decline, and insulin to glycogen ratios promote a shift towards fatty acid oxidation. Additionally, doing the lowest intensity training before consuming any food for the day is said to increase the body's ability to tap into triglycerides more easily and use them more efficiently. So, in summary, metabolic flexibility allows for the more efficient use of triglycerides as a source of fuel for both training and racing, as well as pushing out a substrate crossover point. Fat oxidation can supply energy up to high intensities of our exercise. This has the consequence of reducing the demands for carbohydrates by the body and therefore reducing the effects of carbohydrate deficiencies as well as lactate accumulation. Though these findings are effectively only applicable to exercise at low intensities, where triglycerides are as capable of fueling our intensity demands, the relevance as well as effects of these studies differ dramatically in sports outside of the ultra endurance sphere that require high intensity bursts of exercise. So, what is the counter? As we discussed, metabolic flexibility is the ability for the body to choose a fuel source depending on availability and requirement. Therefore, a major positive to increase metabolic flexibility is the capacity for the body to use triglycerides at slightly higher intensities for a larger portion of fuel requirements in the body. However, this is challenged by the concept that there is no intensity that the body should choose to use triglycerides over glycogen. Further, by training the body to increase its ability to use triglycerides, the consequence is a decrease in glycogen availability and efficiency in carbohydrate oxidation, as well as the use of glycogen when required. One study found that by adopting a high fat diet, subjects were quick to see rates of fat oxidation increase. However, it was apparent that this blunted carbohydrate oxidation at higher intensities, resulting in declined performance economies at these higher intensities. Another study found similar evidence in the reduced ability to oxidize exogenous carbohydrates following regular training with low carbohydrate diets. As such, there is evidence that by increasing the body's ability to use fat, triglycerides as a source of fuel, or fat oxidation, there is blunted ability in carbohydrate oxidation. It is worth noting that many of these studies conduction make mentions of the difficulties in sustaining the control variables and sustained monitoring of subjects. There is limited research here into the longer term effects and the longer term effects of adherence to these options. Additionally, there is evidence to suggest that levels of metabolic flexibility in professional endurance athletes may take over 10 years to develop, which is uncharted territories for, for durations for studies like this. As we discussed, there remain limitations in sustained monitoring and controls of variables. However, there are principles that become apparent that we can draw on. The first is that there is no substitute for when carbohydrates are absolutely required. As such, optimal performance requires a level of carbohydrate intake. We know that carbohydrates remain requirement at all intensities and does remain an almost exclusive requirement when we push past 100% of VO2 max. However, in the context of ultra endurance sport, where intensities remain at about 45 to 70% of VO2 max for longer durations, we can begin to see benefits in increased fat oxidation shining through, particularly when there's very little event that these intensities are breached. Particular benefits include an almost infinite store of triglycerides, preserving glycogen stores, and mitigating levels of fatigue and exhaustion associated with carbohydrate deficiency. A reduced production of blood lactate as the body fuels more of its fuel requirements through oxidation, and a more efficient ability to perform fat oxidation, resulting in more efficient fueling. However, because we cannot overlook the vital importance of carbohydrates, various nutrition plans have been offered to increase the body's metabolic flexibility and ability to capitalize on triglycerides while still maintaining carbohydrate levels to support protein muscle synthesis and ensuring adequate glycogen stores for top-end intensities, allowing the body the ability to freely choose between fuel sources and availability. Some of these propositions include high-fat, low-carb diets during off-peak training blocks, that is, enhancing our fat oxidation during base fitness or aerobic blocks where carbohydrates is less required, and training fasted, specifically referring back to our intermittent fasting discussion before, though consuming glycogen throughout the day to support recovery and glycogen replenishment. The ultimate outcomes of these studies remain relatively inconclusive, and there are several limitations at play, particularly study bias, limited ability to control variables for extensive studies, and the length of adherence required for maximum gains. As such, suggested blanket correct answers at this stage can only be described as an oversimplification and lacks consideration for the circumstantial variables and personal requirements of each athlete. That said, current findings certainly do provide promise that there could be sustainable gains found in increasing metabolic flexibility for endurance athletes. Thank you.